It's a pleasure to be here today. And I think there's really no secret that many states are continuing to be challenged by long lists of scour critical bridges, certainly testify Jean-Louis' presentation and other presentations you'll hear throughout this conference. Certainly what I hope to present to you today is how New Jersey has handled that, how we are responding to that challenge, and also possibly give other states some tools that they might utilize to follow what we're doing. Before I begin, I'd just like to acknowledge I have two of our research partners here today. Unfortunately, they won't be presenting with just a 20-minuter, but we have B. Hunt over there, just to raise your hand so you can see her, and you're going to ask her all the tough questions later. And also, similarly, Brian Shields from Mott McDonald. I'd like to get a few quick acknowledgments in here. Funding for these research projects that we'll present provided by NJDOT. I'd like to give certainly an acknowledgement to Eddie Germain, the state bridge engineer, very, very instrumental in this work. Also FHWA and Dave Henderson, Eric Brown and Paul Carty, who provided a lot of insightful review and input throughout the process of this research. We've also been well supported by a number of USGS scientists, especially Kara Watson and Stephen Benedict. So really our goal here was to develop a rational tool for evaluating the scour at existing non-tidal bridges in New Jersey. And we did this really with a two-step grant process. The first task order was really developmental. The second one was implementation. We did a beta test to bring it to the state of practice. So today I'll talk a little bit about the motivation and background, how the model works, how we input parameters, give you a brief worked example, and also give you an update as to the implementation of the model. Here's a familiar story, I expect. We've been talking about this. This is a bridge down in South Jersey, one of the many on the scour critical list. You can see that we did a very thorough study of that, noting where the stream bed was in the stage 2 studies about 15 years ago, where it is currently. We took into account infills, of course, and we basically found that the actual observed scour at this structure was 1 foot, and it had seen 106% of the Q100 storm. This is what the stage 2 study predicted by applying the HEC 18 equations, 13 feet of scour. Clearly there's a disconnect, part of the motivation for our work and others as well. Continuing on that same theme, here's a stream bed. That rule there in the picture is 4 feet long, and that small yellow dot that the arrow points to is the actual grain size, the D50 that was used in the scour analysis. Clearly, there was an overestimation of scour at this bridge. Okay? This particular course bed continued for some depth. On another similar kind of overestimation, this is a bridge where the stage 2 acknowledged that the spread foundations were embedded about 2 feet or more into rock, yet the actual analysis just focused on the veneer of sediments and the scour of those. So we learned really two important things from these 3 bridges and the other 162 bridges in the stage 2s that we reviewed. And that was number 1, that clearly better protocols for scour evaluation were needed, and number 2, a better decision-making process was essential. This was basically our genesis of the scour evaluation model. We like to describe it as a holistic approach, similar to these days, of course, in the medical field. You would like to think that your doctor is looking at you more holistically rather than just 1 or 2 parameters when you go to the office. And that's really what this model intends to do a thorough review of many aspects of the bridge. So it ends up being a risk-based decision-making tool, provides standard protocols. Past performance and longevity are considered in accordance with FHWA guidance. We try to think it discerns more precisely those bridges that are scour critical from those that are not. It does prioritize the bridges. It also provides specific recommended actions. And although the model right now reflects New Jersey's geology and hydrology, a lot of the model is generic and is not dependent on the state of New Jersey, and certainly is adaptable to other regions of the country. So there's 8 basic input parameters into the model. Erosion classification of the stream bed, that is, what is the nature of the geotechnical materials and how quickly can they erode. What's the age of the bridge? Has the bridge seen substantial scour yet? Yes or no? Has the bridge yet seen the 100-year flow? Yes or no? Does the channel appear to be stable? We also will perform certain stability checks using either calculated or assessed conditions. Could include HEC 18 equations, could include the envelope curve method that's been developed by Stephen Benedict down in South Carolina. We did a side study to confirm its applicability to some of our regions in Jersey. And also, sometimes you have to just go with empirical methods when there's not a lot of good number crunching available. We also assess importance of the bridge and also whether there's particular structural vulnerabilities. So this is the master flow chart. There's basically 6 modules, and the first module is the geotechnical risk evaluation. What that basically considers, it starts with a very thorough geotechnical reconnaissance study. I'm a geotechnical engineer, so certainly I made sure that was the case. But you learn a lot about the bridge, about the geology and the conditions upstream, downstream, and at. A thorough field scour investigation. This will yield certain input queries to the model, things like the erosion classification of the stream bed. Is substantial field scour present? What's the age of the bridge? Among other things. That is then input into the module, and it will yield whether that bridge is a low risk geotechnically, medium risk, or high risk. Usually in parallel with this, module number 2 is the hydrologic hydraulic risk analysis, and really the heart of that is a 100-year storm check. We have chosen the 100-year storm as kind of our risk dividing line, very similar to what the previous edition of HEC 18 used, and we still feel for existing non-tidal bridges it's a reasonable thing. Of course, that can be adjusted in any application. The kinds of input queries that then come into account would, of course, be the percent seen by the bridge to date, the percent of Q100. Substantial scour still plays a role, whether it's present or not, and certain scour stability checks calculations may also be performed. Once again, output low, medium, or high risk. Okay, the third module puts the results of the first 2 modules together. And we use for this what's called a risk decision matrix, something you've seen before throughout science literature and even in management has adopted these, where basically we have 2 axes. We have the geotechnical risk on the x-axis there, the upper one. Oops, going back. Let's go back one. We have geotechnical risk on one axis. We have hydrologic hydraulic risk on the other axis. That leads you to one of 4 priorities. Obviously, if you have high geotechnical, high hydrologic risk, that is a priority 1 bridge. Priority 1 means fix it as soon as possible. On the other extreme of the priority levels, we have priority 4 bridges, which are low-risk bridges. Those are bridges that are candidates for removal from the Scour critical list. We have 2 other intermediate categories of risk that kind of reflect reality in our business. Priority 2 is a bridge that's also at risk, but probably more of a continuing maintenance headache rather than a bridge you would worry about in the next major storm. That could be repaired, possibly long-term monitoring a solution there. Priority 3 is one of those gray areas where it's really a low-risk bridge, but there's some aspect of it that we're not comfortable with, either requires more study or possibly a directed maintenance and repair at one aspect. That establishes what we call the technical risk of the bridge. The next 2 modules may adjust that risk. The module number 4 is the bridge importance analysis, where we try to see within the inventory in the state how important is this bridge. Certain bridges, such as a interstate or an evac route along the shoreline, will automatically default as important. Other things that can make a bridge important is just a high ADT, or a very, very long detour length, or a very, very large and long and important bridge. These are things. If the bridge is found to be important, it elevates the technical risk by 1 unit. So for example, if the bridge had rated technically as a priority 3 and you find it to be important, it now becomes a priority 2. In a similar manner, module number 5 does a kind of a structural vulnerability check. Well, we do get structural engineers involved, should be involved in most scour analysis anyway, but we're really looking for the obvious, say, aspects of a bridge that might increase scour risk, such as just a double stringer support system, or maybe individual columns on individual piers. Things that really, if there should be any compromise from scour, these are bridges that can really come down quickly. On the other side of the coin, we have certain types of structure systems that decrease scour risk. Most obvious maybe being pile foundations. There can be other things, solid wall piers. There's certain systems that actually you would prefer if the bridge begins to be compromised by scour. Again, these may adjust the technical risk. They only will elevate it. These two other factors never will decrease it, but they may elevate it and make the bridge more important to fix as quickly as possible. The last module basically puts it all together, and as we mentioned earlier, there's priority 1, 2, 3, and 4. The priority ones, it's very definite what you will do. You'll fix it as soon as possible, continue the flood watch of that bridge until that's accomplished, and once it is fixed, you'll return it to the 2-year NBIS inspection. Priority 4, the other extreme we mentioned, candidate for removal from the list. We also have priority 2 and 3, which have very, very definite actions that DOT will take, very similar to what any other agency would do. So that's really the overview of the model. Some of the, let's say, improved protocols that we've developed. This is our erosion or stream bed classification system we've developed. If you've ever, certainly know the Unified Soil Classification System. If you include the dual classifications, there might be 25 or more different classifications of soil, but if you ever walk stream beds, you'll find out you walk 50 feet, you'll probably see at least 3 or 4 of those. So we've kind of simplified and grouped the typical types of river sediments into 7 categories of classification, ranging from sound rock, weak rock, extremely coarse particles, and then down into the more classical granular and clay soils. And these are some examples of at least 4 of those 7 classification systems. We also have give a lot of guidance in how to come up with that 100-year storm check. I think Jean-Louis said appropriately that sometimes that's not the easiest thing to do. So we have our technique there as well. We basically have 4 different cases. The best case is 1 or more gauges on the stream with a lot of record, and then there's other cases. But we provide different options for trying to come up with that Q100 number for that particular bridge location. We also have a standardized scour inspection form for field inspectors that prompts them to specifically look at many, many aspects of the bridge that are not really contained on the NBIS form or some other documents that states may use. Okay, so let's go through a really, really quick example. This happens to be a bridge. It's the one with those real coarse particles you saw in the beginning. It was built around 1933. It's about 170 feet long, 3 spans, concrete spread footings. So this is kind of how the model plays out. Very, very, very brief. Usually this is explained in a 20 or 30-page report. But basically, as you can see, we thoroughly review every available piece of information for the bridge, also any of the history of fascia soundings that are available. We then also do the field scour investigation, which verifies the stream bed classification. This particular one was a G1, which means that it's mostly cobbles and boulders, a very coarse bed. Check the channel findings here. It was a laterally stable, and scour observations, really just some minor degradation and aggradation. Continuing on down the line, this is what and I see the 5-minute, it's the 5-minute signal, right? This is what the flowchart for the geotechnical risk analysis looks like. I won't speak too much about it to allow time, but you can see basically working through this In this particular case, it was a G1. That prompts actually a scour stability check. In this case, two HEC 18 equations were used, the NCHRP 2420 and the coarse particle equation. Both came out okay for that bridge. Continuing on down the line, has the bridge seen substantial scour? Answer was no. This ultimately leads to a geotechnical risk of low. Let's take now a quick look at the hydrologic model. And here we mentioned previously that the heart of that is the 100-year storm check that was checked for this bridge. It had seen 101% of the 100-year storm, so the conclusion was yes, it had seen the storm. We then go into the hydraulic flow chart in a similar manner. We're using some of the input factors such as the erosion class, the finding of the 100-year storm, and also whether substantial scour is present. And basically the conclusion is this was a low hydrologic and hydraulic risk. Put it all together now into the risk decision matrix. Low and low leads us to a scour priority 4. And a final check of the adjustment. This bridge had no special importance within the inventory, and it was found to have really no major structural vulnerabilities, no change in scour priority. So the final conclusion was this is a priority 4 bridge. We also provide guidance on how to code the bridge using the item 113. So let's get to the bottom line here. About 2 years ago, we embarked on an implementation phase to bring the model to practice. We went out and did 19 scour critical bridges. We had 3 participating consulting firms. B. Hunt and Brian Shields were part of that team. They were the leads on their projects. And basically, we stress tested this model over the entire state, starting from the northern tip where the Appalachian Mountains and the hard beds are predominant, all the way down to the south where we have coastal plain sediments unconsolidated, and everything in between. New Jersey is a very small state, but we're a very complex state geologically. We have it all, and actually it's very easy to teach geology courses as a professor in the state because you just have to drive an hour in each direction and you can find every possible condition you could imagine. We also had lots of other characteristic changes. These is what the bridges looked like, kind of the standard 40, 50, 60, 70-year-old bridges you'll find in almost any inventory. And this is what our results came out to be. Out of the 19 bridges, we found actually 5 of them were priority 1. They were immediately put to the project management people at NJDOT for immediate action for design and repair. We had 2 priority 2s, a little more of a delay in response to those, and we actually had 10 bridges priority 4, which basically means those 10 bridges, examining other aspects that there might be reasons other than scour that those bridges are going to be replaced or repaired, but 10 of them from a scour perspective were deemed adequate. We often are asked, some final notes, how did we develop this model? We consider it an expert system, and you may know that an expert system is really a very, very narrowly focused problem-solving tool, say in the field of AI, artificial intelligence. Our objective was to try to mimic the kinds of judgments and analysis that an experienced scour engineer would undertake. The data techniques used, just FYI, usually forward chaining, that is starting out with facts, going through a decision process, and coming to a conclusion. That's how expert systems like SEM function, but how are they developed? They're developed by backward chaining. And that's how we did it, where we start out with conclusions. We know this bridge is good and this bridge is not good. We wanted to make sure that the input parameters and the decision process were leading to the correct solutions. Having said this, you can see that although it was developed in the state of New Jersey, it's the one we're using now, most of the model is generic because it's related to the erosion classification of the materials. So really it is adaptable given the diverse geology of New Jersey. It is fairly adaptable to other states and regions, and certainly if anyone would like to have a conversation with us or to review our documents. And here's some of our publications. I I assume the presentation will be posted online. You could check, these are our research reports over in recent years. You're welcome to read about all the development and implementation of the model. Also, I brought this up not to forget it. We've recently been tasked by NJDOT to actually create, rather than a research report, an actual applications guideline, a how-to manual. It's still in the draft stage, but we have some copies of it here today. Anyone's like to take a look at it, or certainly email me, and we can, if you can't find these documents, we'll send you the links, as well as a draft link to the Scour applications guideline. So, how are we doing on time? About right?
We're good. Yeah, we got
Okay.
time for questions.
Good presentation. Oh, that's loud. The last two presentations then too, especially with the observed scour, how do you account for channel migration or long-term degradation? Does it take those two aspects separately from contraction and more event-based scour?
Well, let's say the channel migration is really part of our stability check to try to determine whether there's indicators that it's starting to move laterally or either incipient or already has occurred. The degradation and aggradation, or the degradation specifically, we use some of the traditional methods of analysis there. We obviously do a very, very thorough field evaluation. It's already been mentioned that infill is always that demon out there that we have to watch. We do, in our inspection method, it's not just a fascia sounding. Fascia soundings are very important, but they don't tell you the whole story. So our protocol involves really probing the stream bed frequently. And any good scour firm that does bridge inspections will do that to try to detect the infills. During our work to try to validate the model, we actually used GPR. We wanted to double check that we were not only feeling a good probe rod, and we do provide guidelines of that in our documentation, how we recommend you do probing to pick up infills, but to really double, triple check that we were actually seeing all the infills in order to calibrate the model. We did use GPR. Basically, we put it into a floating boat, if you will, and traversed the site. We're not the first to do it. We actually learned that technique from Stephen Benedict down in the South Carolina USGS, and he used a rubber boat, we used a plastic boat, but our next iteration of that, if we ever need to do it, is we're going to get a remote control so we can just sit on the bank and do our scour evaluation. But, certainly in a serious note, you have to really check that bed very, very carefully, and some of it just has to be done physically. Any other questions?
All right. Let's thank Dr. Schuring for his
Thank you.
presentation.